Welcome to Ask and Learn.
In this case, we are told that the motor is spinning at the at 20 radians per second, and we know what the unbalanced mass is. Well, we know it's the unbalanced weight, so we can convert to a mass. So we need to find the amplitude of the excitation force, and it is the unbalanced mass times the distance from the rotation axis to the unbalanced mass, or the center of mass of the body that's rotating, times the angular velocity squared. And the angular velocity is really just the excitation frequency. Okay, so again, when you have things rotating, you can think about the rotation speed as also a frequency. So again, how many radians per second does it go around? The eccentricity length was 10 inches, so we convert that to feet, and then the excitation frequency we need to be in radians per second, and it was given to us that way. So it turns out that this thing comes out to be 2.59 pounds. We have the spring constant from before. We know the natural frequency from before, and we can figure out that this is probably not a good speed to be running the motor, because it's pretty darn close to our natural frequency. It's not exact, so we can give it an amplitude here, and it turns out that that amplitude, we can have F naught, we have K, we have omega, capital omega, and we have omega n. So we can plug everything in. It turns out that that is 0.0409 feet, or about half an inch. So that's quite a big excitation for this thing. And again, we don't really have a whole lot of eccentricity. This is not a lot of amplitude here, but because it's near resonance, we're getting quite a big, large motion from this very small amplitude of our excitation force. Again, we can think about it as the static deflection from this, a force of this amount would be roughly, what, 1/600? So, much smaller than this. So that's why this denominator here is actually going to amplify everything. So this thing is going to be a small number, just because this is so close to this and this is so close to 1.